Okay, commercial break over. We're back. Here is a problem that I really, one more time for emphasis, really like. Are you picking up what I'm putting down? All right, good. Here we go. Now, let's say that we have a, what do you call that ice stuff? Ice. We got some ice, a block of ice. We have a block of ice. I'll draw it out. Block of ice, okay, block of ice. And let's say that block of ice is 1 kilogram. 1 kilogram. Now let's say the block of ice is in the freezer. Now a freezer is not at 0 degrees. A freezer is 0 degrees. If your freezer is 0, your ice cream is going to be all mushy. So you're on the verge of melting right down. So freezers are set lower than that. So let's say your freezer is maybe like -5 degrees Celsius. So this ice is in the freezer at -5 degrees Celsius. Okay, so the temperature, I'll write that here, -5 degrees Celsius. Okay, what we want to do is we want to get this ice, this block of ice, to boil. So we're going to get it all the way up to a boiling temperature and vaporize it and boil it away. Our job, figure out how much heat energy that's going to take. Oh, you ready? You ready? Okay, this is your mission. You will do it and you will like it. Okay, that's German physics guy. You will do the physics and you will like it. Okay, here we go. So we're gonna first thing we gotta do though is we have to get the ice cube, which is at -5, to its melting point. It's not melting yet. It's not gonna melt. If we take this out of the freezer and put it in the pot on the stove to boil it, well, it's not gonna start boiling right away, and you know that. It's gotta get to it's gotta melt first, but it's gotta get to the melting temperature. So I'm gonna draw a picture, kind of a picture here for you. So what's gonna happen is the temperature, this is a temperature versus time picture. Kind of a graph, temperature versus time picture. So the temperature goes up, and we get a block of ice, okay, to its melting point. So now we've gone from -5 to 0. Okay, now it's getting ready to melt. It won't melt before that. You gotta get it to its melting point. So we know ice melts at 0. Okay, so now we keep pumping energy into it. How much energy is this gonna take to do this? So we pump energy into it, and it's gonna begin to melt. Whenever, you ready for this? This is important. Okay, you listening? Wake up, stop drooling. Get that, wait, what, like that, ew, gross. Okay, stop drooling. Now pay attention. Whenever you get something to go through a phase change, whether it's melting or freezing would be the other way, if it's vaporizing or condensing, the temperature remains the same. The temperature does not go up while something is freezing or melting or vaporizing or condensing. You know this. No, I don't. Yes, you do. You do. Okay, try this at home. Take some water, boil it. Put a thermometer in it. Read the temperature. Now, what should it read? 100? Yes, it should read 100. All right, come back 5 minutes later. Read the temperature again. What is it now? It's going to be 100. Of course it will be, because the water is boiling. The temperature isn't going up. You're still pumping energy into it, but the water is maintaining a constant plateau, 100 degrees. Where's the heat going? Into breaking the bonds. It's going into breaking the bonds. You know, breaking bond. Bond, I must break you. You will never break me. I am a 007 agent of the Secret Service of the British Empire. Okay, funny. Break bond, get it? Break. Okay, all right. Daniel Craig, I think he's the best. I think he's the best Bond. Okay, you might have your favorite. I have my favorite. It's the way it is. All right, let's see, where was I? Oh yeah, break the bond. Yeah, so what's happening is that temperature is plateaued. Your boiling temperature water is 100, 100 when it's boiling. All the energy goes into breaking those bonds. Remember the screaming, the silence of the lambs? No! That's where it's going. So we plateau during a phase change. So to draw that, okay, so I'm going to melt this. Plateau. So when it comes to melting, all the energy is going into breaking the crystal structure. So you've got this nice hexagonal crystal when it comes to water, and energy is going in and breaking that, forcing that crystal to break down, so we get the floaty water. All right, so now we'll get water. What temperature will the water be at? 1 degree, no, 0. It's plateaued. It'll be at 0 degrees. But that doesn't make any sense. If the water is at 0 and the ice is at 0, how can it be? Well, we're putting energy into the system, so going in, we become water, but it has to start somewhere. It's at 0 degrees. Now, then, you've got the stove cranked up, or even if you take an ice cube and leave it on the table, the ambient air temperature is warmer, so it'll melt it and then start to increase its temperature. Okay, so now its temperature will go up to what? Now the boiling point, 100. So 100. Then we got to vaporize it. We got to boil that water away. Plateau again. Okay, nice flat temperature, 100 degrees. And then it becomes steam at 100 degrees. Steam at 100 degrees when it vaporizes. The thing is about steam at 100, if you get blasted by steam at 100 degrees versus putting your hand in water at 100 degrees, okay, don't try this at home for professionals only. I've been trained. Put my hand in water, boiling water, it hurts, painful, okay? Trust me, trust me. Steam is worse. What? Why is it worse? The steam temperature shouldn't be any worse. It is, because you see the steam, what's going to happen, if steam at 100 degrees hits your hand, ouch, 100 degrees, but then your hand is cool compared to the steam. So the steam will condense. It'll turn back into water on your skin, releasing all that vaporized and all that energy, that heat of vaporization now goes into your skin. So it releases energy when it goes from the gas phase back to the water phase. It has to gain energy to go from here to here, but if you're gonna go back and it hits your skin and it cools and condenses, you lose all that energy into the environment, which happens to be your skin. Ouch. Again, don't try that at home. Trust me on that one, okay? All right, so more painful, the steam burn at 100, even though it's the same temperature. Let's do the math on this. Okay, this is bookkeeping. Keep things organized, and this problem isn't really that bad. You just have to keep things organized. Now, each line represents a step. This is a step in the solvation problem. No, you cannot do this all at once. Can I use the heat equation? Because the heat equation says M delta T Cp. And with heat equation, we have a starting temperature and a final temperature, delta T. I have the mass of 1 kilogram, and I'll put the specific capacity of water in here. That'll work, right? No. No. Two reasons. One, during here, you don't have a temperature change. Ain't gonna work. Second, the specific heat of water is not the same as steam or ice. Boom, they're different. So each step has to be taken individually, and then in the end, add them all up. All right, step one, line one. Step two, step three, and step four. Okay, here we go, dive in, keep organized. Let's see, where I can do this. This first step here, from here to here, that's a temperature change. If you have a temperature change, there's your equation. So for step one, I'm gonna use that equation. I'll do the math over here. Okay, I'm gonna write down step one. Can you see this? Yeah, you can see that. Okay, so Q is equal to M delta TCP. The mass is 1 kilogram, so 1. Change in temperature in step one is -5 to 0, so it's a change of 5. We don't care about the negative, we just want the change. So change is 5 degrees. So 5. And I need the specific heat capacity of ice. The specific heat capacity of ice, you look it up, it's 2100. 2100 joules per kilogram. So 2100 goes there. Now, if I do the math on that, I'll get the energy it takes to get my ice up to the boiling temperature. All right, let's do that. Well, let's just crank that out. Actually, we could do that without a calculator. 1 times 5 is 5. 5 times, that's 10,500. So step one, it'll take 10,500 joules. See if you can still see that. You can. I'm going to turn you just a little bit so you can. There we go. All right, so step one, done. Step two. Now, during step two, you do not have a temperature change. That ain't gonna work. You put a 0 in that and you get 0 heat, which is stupid because you're melting the ice, so you gotta be putting heat into it, so that ain't gonna work. How am I gonna do this? We use what's called the heat of fusion equation. Very simple equation. Here it is. The heat, so I'm gonna put Q, that it takes to fuse, the heat that it takes to fuse, which means melt, the heat that it takes to melt is equal to the heat of fusion times the mass. Now, heat of fusion is in joules per kilogram. Mass is in kilograms, so the mass units will cancel. It'll leave me with joules. Boom, I get the amount of heat it'll take to melt that ice. So I gotta put the right units in there. So let's go right down here. QF equals heat of fusion. Now, we went over that in the last video. You kids all remember 1/2 evil? You remember that, 333. Add 3 zeros for kilograms. So that's 3, 3, 3, 0, 0, 0. joules per kilogram. And we have 1 kilogram. Made that easy on you, huh? Who's your favorite physics instructor? Well, I made that easy. I'm with you. Yeah, this guy. Okay. So 1. All right. Do the math. Anybody got a calculator? Get the answer. All right. That's going to be, you can still see this, 3, 3, 3, 0, 0, 0 joules. Nice. All right. So now we've got our water because we just melted the ice. We got the ice up to melting temperature. We melted it. Now we're going to get it up to the boiling temperature, step 3. Now step 3 does have a temperature change. So we can go back to our heat equation and use that. All right, so let's see. Q is equal to heat equation. Mass, 1, times delta T. Well, that's 0 to 100. Subtract them. Again, calculator, anyone? Anyone? Billy? 100. Thank you, Billy. So that's 100. And now this is water. Water. 4190. That's where we use the 4190. 4190 for water. Okay, up here we use the ice because it's ice. Here we're going to use steam because it's steam. Actually, we don't have to use steam. If we wanted to get the water steam to 120, then there would be a temperature change, and we would use the specific heat capacity of steam, which is 2010. 2010, good year, 2010 was. Yeah, we'd use that, but we're not getting the steam to a higher temperature, so we don't have to worry about, in this problem, the heat, or the specific heat capacity of the steam. Okay, moving on. Let's do the math. So this is easy, okay? I'm here for you. I make the math easy. So this is 100 times this, 41900 joules. So 419 joules. All right, last step. Oh, thank goodness, you're so tired of this problem. Now we got to vaporize. Let's vaporize. See what happens now, huh? So this is not a temperature change. So once again, I can't use this equation. I'm going to use the same idea that I had here. I'm going to use Q, the heat to vaporize, QV, is equal to the heat of vaporization, that's HV, times mass. All right, here we go. So the heat to vaporize equals the heat of vaporization. Remember that? That was that big number. That was the 2.260 million. Million. Austin Powers. Good movie. You haven't seen it? Go watch it right now. I'll wait. Okay, watch it. Awesome. Great. You're caught up now. So this is 2.60000 joules per kilogram. A lot, huh? And the mass is 1 kilogram. So again, I'm here for you. Made the math easy. Multiply. Get that as 2.60000 joules. Now we have all 4 parts, all 4 steps to get our cold block of ice to nice 100-degree vapor. Okay, so it's now floating around vapor. What's the total amount of heat it takes? Add them up. Okay, you can do that. Okay, I'm not going to do that for you. I'm not, okay, you know what? I will. Okay, fine. I'm here for you. You've had a rough day. You relax, okay? I want you to be nice and comfortable. You sit back. So let's do the math on this. So 10,500 plus 333,000 equals plus, oh, don't divide. No. Okay, equals, and then, oh, actually, hit divide again. 2.60000. Okay, whoa. That's 10,22500. So the total amount is 10,225. Wait a minute. Wait. 2, 3, 1, 2, 3. Oh, I must have screwed it up because I did hit the divide. I screwed it up. No, that's wrong. Okay, stick with me, okay? You kids sitting back there laughing while I do all the work. Oh, don't you quit on me now. The numbers are fading. Don't you start. Don't do it. Don't do it. No, it's doing it. Don't do it. And and then plus our 10,500. Come on, don't, oh crap, I don't know what that number is, because okay, let me figure it out then, because it's killed, the last number died, and the one on the left, so I'm not sure what it is. So that's 500, what is that supposed to be? You know, I'm gonna do this in my head then. All right, so that's 2.6, 2.7, 2.8, 2.9, 3. It's supposed to be a 3. I think that's what that's supposed to be, even though the number's gone. It's supposed to be a 3,019,500 joules. Okay, my calculator doesn't say that because it's crapping out on me. The number on the left is crapping. So I think that's supposed to be what it is. And that makes sense. This is 2 million, 2.2 million, 2.6 million, 3 million and change. So that does look right. That looks right. Okay, I'm sorry it took so long. All right, you know, I'm here for you. You relaxing. Did you get some popcorn? Okay, go eat some root beer and drink some popcorn if you're getting bored, okay? What I do want to point out about this, though, is this. Out of this 3 million joules that it takes to do this job, that's the total amount. Almost 2.3 million, or around, you know, that's like what? That's, 2 million, that's like 67%, about 2/3, about 67% of the energy it takes to do this happened right here. Do you remember why? Do you go back to the last video? Remember why? Because we're breaking that hydrogen bond, and it doesn't want to do that. They like each other. So if you want to break that hydrogen bond, it takes a lot of energy to do that, and hence the huge number here. Matter of fact, that's more than these combined. The other 3 steps combined, that's significantly more than the other 3 steps combined. And here's one more fun fact for you. This is a huge amount of energy. So when something condenses, it releases that energy. So we already talked about on your skin, you get a steam burn at a particular temperature. It's much worse than just putting your water in your hand. Got it backwards. Putting your hand in the water at that temperature, because it's releasing that energy onto your skin. Bad. The other thing is too is hurricanes or himicanes. Okay, himicanes like Hurricane Frank, Hurricane Gertrude, or whatever. Right? Those function because of this energy. Water rises out of the ocean, all right? It condenses in the atmosphere, so water vapor rises and condenses. And when it condenses, it goes to the condensation, it releases all that energy. All that energy becomes the heat engine, the engine that drives that hurricane. So, yeah, so if you live on the south or east coast in the south, you're not happy about this heat of vaporization sometimes, because it's gonna smack you in the face. Okay, that's about enough of that. So this is a really good problem. Again, I really, really like it. Do it, do it, do it. Make sure you know this problem. Okay, all right. Talk to you soon. Good talk, by the way, good talk.